Welcome to Thought Frontier.
Hey everyone, today we're diving deep into antimatter.
Okay.
And trust me,
Mm.
it's way more than just the opposite of matter.
Right.
We're going to unpack two really cool papers to help us understand.
Sounds good.
One is by David John Baker and Hans Halvorson called Antimatter.
Kitschy.
And the other one is
Yeah.
called Matter and Antimatter in the Universe by Laurent Canetti and his team.
All right.
So basically, we're going to try to bust some myths
Yeah.
and really get to the bottom of what experts know about this mysterious stuff.
Definitely a journey into some big questions in physics.
Totally.
Yeah.
I mean, everyone's heard of antimatter,
Right.
but who really understands it?
Yeah.
Let's start with the basic picture we all learned in school.
Okay.
You know, the electron and its antimatter twin, the positron,
Mhm.
same mass, opposite charge.
Mm-hmm.
Seems simple.
Right? That's the textbook picture.
Right.
And it's a decent starting point.
Mm-hmm.
Baker and Halvorson even describe it in their paper.
Okay.
They talk about how this idea comes out of those cool relativistic wave equations,
Oh, yeah.
like the Klein-Gordon equation.
All right.
But
Here comes the weird part.
yeah, exactly.
Yeah.
This neat and tidy picture kind of falls apart when you really dig into quantum field theory.
Oh, no.
Things get much more complex and, dare I say, more interesting.
So lay on me. What's wrong with the simple picture?
Well, in quantum field theory,
Okay.
the idea of particles as these tiny things with definite properties like charge,
Okay.
it gets a little blurry,
Yeah.
especially in interacting quantum field theories, which is how our universe actually works. This
Right.
whole idea kind of breaks down.
Wait, so are we saying particles don't exist?
Not exactly.
What's
It's
that?
more that our usual way of thinking about particles
Mm-hmm.
as these little points with specific properties
Right.
doesn't really capture the full reality described by quantum field theory. There's not always a clear way to count or define individual particles.
Wow. Okay. My head is spinning already.
Yeah.
So if particles are so fuzzy,
Yeah.
how do we even define antimatter then?
That's when things get really cool.
All right.
We need a more general framework.
Okay.
And that's where super selection rules come into play.
Super selection rules.
Yeah. Think of it like this.
Yes.
Imagine there are these fundamental no mixing zones in the quantum world.
Right. Yeah.
Super selection rules are like walls
Okay.
that separate certain types of quantum states.
Mm-hmm.
So they say you can't have a mix
Okay.
or a superposition
Yeah.
of states with different charges,
Okay.
like matter and antimatter.
So like matter and antimatter are in separate rooms
Exactly.
and there's no way to combine them.
That's a great analogy.
Okay.
These separate rooms are called sectors.
Sectors.
Each sector has states with a specific charge, and they're dynamically isolated,
what does that mean?
meaning the laws of physics stop states from hopping between sectors.
Oh, so like a matter state can't just suddenly become antimatter.
Exactly.
Yeah, okay.
So even though the particle picture is a bit shaky,
Yeah.
these sectors keep matter and antimatter distinct.
So it all makes sense.
Yeah.
But there's something I've always wondered.
What's that?
Why do some properties get flipped in antimatter, like charge,
Right.
but others, like isospin, stay the same?
Ah, that's a great question.
Yeah.
And the answer lies in something called the gauge group of the theory.
Okay, gauge group.
Yeah.
Now we're getting into the abstract stuff.
It's where the mathematical structure reveals the deeper rules.
Okay, can you break that down?
Think of it as the set of symmetries
Okay.
that governs a particular force.
Okay.
For example,
Hmm.
gauge group U1 describes electromagnetism,
Uh-huh.
and it explains why electric charge is quantized.
Okay.
It comes in these discrete units,
Right.
and why it slips for antimatter.
So the type of symmetry dictates what gets flipped.
Exactly.
Okay.
And for more complex forces, like the strong force,
Mhm.
the gauge group is more complicated.
Okay.
And it's how these groups are represented mathematically.
Right.
We call these conjugate representations.
Okay.
And they explain why certain quantum numbers flip while others stay the same.
Wow. So it's like the gauge group is the blueprint,
Okay.
and these representations are different ways to build from it.
Yeah, that's a good way to think about it.
Right.
And this leads to a really mind-blowing result.
Okay, what is it?
The Doppler-Roberts reconstruction theorem.
Okay, I'm listening. What's so mind-blowing about it?
It says that from the math of a theory,
Okay.
specifically the structure of its superselection sectors,
Mm-hmm.
you can actually reconstruct the properties of particles and antiparticles.
Whoa, wait. So we can figure out antimatter just from math?
Pretty much.
That's crazy.
It's a deep connection between the abstract math
Yeah.
and the reality of particles and antiparticles.
I'm seeing why antimatter is so much more than just opposite matter.
Right.
It's like a window into the structure of reality itself.
Exactly.
And this new understanding gives us a much more fundamental definition of antimatter,
Yes.
one that goes beyond particles.
Absolutely.
All right, so we've learned that antimatter is a lot more complex than just opposite matter.
Right.
You've got these sectors keeping matter and antimatter separate, and this crazy theorem that says we can basically figure out antimatter just from math.
Yeah, it's pretty wild.
But there's a big question bugging me.
What's that?
If antimatter is so fundamental,
Yeah.
where is it in the universe?
Right.
Shouldn't the Big Bang have created equal amounts of matter and antimatter?
That's the million-dollar question.
Yeah.
And it's what Laurent Canetti and his team tackle in their paper.
Okay.
The simple answer is we don't see tons of antimatter out there. Our universe seems to be mostly matter.
So no antimatter galaxies
Not that we've seen.
or antimatter stars?
Nope.
Oh, man. I was kind of hoping for a whole antimatter universe.
It's a cool idea.
Yeah.
But observations from cosmic rays, gamma rays,
Mm-hmm.
the whole electromagnetic spectrum, basically, they tell a different story. They put really tight limits on how much antimatter could be out there.
What about like a more subtle mixture?
Okay.
Could there be pockets of antimatter scattered throughout the universe?
Like at the atomic level.
Yeah.
That's another scenario they looked into.
Okay.
They looked at something called the cosmic diffuse gamma ray background.
What is that?
It's basically a faint glow of gamma rays coming from everywhere.
Okay.
And this background would be much brighter if there were lots of antimatter constantly annihilating with matter.
Oh, I see. So what did they find?
Their findings are pretty clear.
Okay.
The amount of antimatter in the observable universe is super tiny,
Like how tiny?
about 1 part in a billion.
1 in a billion. So the universe really did pick a favorite.
It seems that way.
But why? What happened to all the antimatter?
This is what we call the baryon asymmetry problem.
Baryon asymmetry.
So the Big Bang nuclear synthesis model,
Okay.
which explains how the first light elements formed,
Right.
it tells us that for every billion photons, you
Yeah.
know, those particles of light left over from the Big Bang,
Mm-hmm.
there's roughly one baryon.
Baryons being protons and neutrons, the stuff that makes up atoms.
Exactly. And that tiny ratio.
Like 1 baryon for every billion photons.
Yeah.
That's wild.
It reflects the tiny excess of matter over antimatter that survived the Big Bang.
Wow. So it's incredibly small,
It is.
but it's everything.
Yeah. Without it, we wouldn't be here.
So we have a universe full of radiation, these
Yeah.
leftover photons.
Right.
And for every billion of these photons,
Hmm.
there's just one tiny piece of matter.
Yeah.
Like finding one specific grain of sand on a whole beach.
It's a mind-boggling thought.
Yeah, it is.
And the big question is, how did we end up with this tiny but crucial excess of matter?
Yeah. That seems like a pretty big challenge.
It is.
Can our current theories even explain that?
So that's where things get even more interesting.
Okay.
The standard model of particle physics,
Mm-hmm.
which has been super successful in explaining so much about the subatomic world,
Right.
it actually struggles to fully account for this asymmetry.
Wait, you're telling me the best model we have can't explain why we exist?
Well,
There's got to
yeah,
be a but coming.
there is a but.
Okay, good.
While the standard model can't quite explain the amount of matter we see,
Yeah.
it does give us clues about what a successful explanation might look like.
Okay, I'm all ears. What are the clues?
Back in 1967,
Okay.
a physicist named Andrei Sakharov,
Mm-hmm.
he laid out 3 conditions
Okay.
that any theory explaining baryogenesis,
Sure.
the creation of this baryon asymmetry,
Okay.
must satisfy.
So like a cosmic checklist for a successful universe.
I like that.
Yeah.
You need processes that violate baryon number.
Okay, what does that mean?
That means reactions that don't conserve the total number of baryons.
Gotcha.
Then you need processes that break something called CP symmetry.
CP symmetry.
Basically, the laws of physics have to operate differently for particles and antiparticles.
I understand.
And finally,
Yeah.
you need something called a departure from thermal equilibrium,
Okay.
a state of imbalance.
So those are the rules.
Yeah.
But how does the standard model stack up against these Sakharov conditions?
It actually checks all the boxes.
Really?
Baryon number is violated by processes called sphalerons.
Okay.
CP symmetry is violated in weak interactions.
Mm-hmm.
And the expanding universe provides a departure from thermal equilibrium.
So we're good. Case closed.
Not so fast.
Oh.
The standard model, while fulfilling the conditions,
Okay.
it falls short in the details.
Like so.
The amount of CP violation it predicts,
Mm-hmm.
it's simply too small to explain the observed baryon asymmetry.
Oh, so it's like having the recipe, but not enough of a key ingredient.
Exactly.
So are we back to square one?
Not necessarily.
Okay.
This shortfall actually points us towards new physics,
Oh, okay.
beyond the standard model.
Okay, so new particles, new forces, that kind of thing.
Exactly.
That's kind of exciting.
It is.
It means there's a whole new frontier of physics out there.
Absolutely.
Just waiting to be explored.
And some of the most promising candidates for explaining this baryon asymmetry,
Yeah.
they come from areas where we know the standard model's incomplete,
Like where?
like neutrino physics and dark matter.
Neutrinos and dark matter.
Yeah.
Okay, I'm intrigued.
Yeah.
Can you give me a sneak peek into how these might be connected to the missing antimatter?
One idea that's gaining a lot of traction is baryogenesis from sterile neutrino oscillations.
Sterile neutrino oscillations.
Remember those sectors we talked about?
Yeah.
Well, these sterile neutrinos,
Mhm.
they could be the key to bridging the gap between sectors, allowing for processes that ultimately favor matter over antimatter.
So these sterile neutrinos are kind of like rule breakers.
You could say that.
All right, tell me more.
They are pretty fascinating.
Okay.
They might hold the key to solving not just one,
Okay.
but several big mysteries in physics.
Okay, I'm hooked. Remind me,
Yeah.
what are sterile neutrinos exactly?
So
And how do they fit into this whole baryon asymmetry thing?
sterile neutrinos are hypothetical particles.
Okay.
They're like heavier cousins of regular neutrinos,
Mm-hmm.
but they interact with the rest of the universe even more weakly. So weakly that we haven't actually detected them directly yet.
Oh, wow. So they're like ghost particles.
Yeah, that's a good way to think about it.
Just flitting through the universe.
Yeah.
Without leaving a trace.
And because they interact so weakly.
Right. They're not bound by the same rules as the particles in the standard model.
Okay.
This gives them a unique freedom to behave in ways
Yeah.
that could explain things like the matter-antimatter imbalance.
I see. So they can kind of slip through the cracks
Yeah.
of the standard model
You got it.
and do things other particles can't.
Exactly.
But how do they actually tip the scales towards matter?
Okay.
It seems like a big leap. The Canetti paper looks at a specific model
Okay.
called the Neutrino Minimal Standard Model,
Oh,
or
yeah.
MSM.
All right.
And in this model, sterile neutrinos can do this cool thing
What's that?
called oscillation.
Oscillation.
Yeah, they basically change their identities as they travel through space.
Oh, wow. So they're like chameleons.
Exactly.
Right.
And here's the crucial part.
Okay.
These oscillations can violate CP symmetry,
Uh-huh.
one of Sakharov's conditions for baryogenesis.
So they're breaking those cosmic rules.
They are.
But how does that actually lead to more matter than antimatter?
Okay, so it's a multi-step process.
Right.
But the key is that CP violating oscillations,
Right.
they create an imbalance between leptons and antileptons.
Leptons being things like electrons and muons and tasches.
Exactly.
Okay.
And then through those sphaleron processes,
Right. We talked about those.
this lepton asymmetry gets converted into a baryon asymmetry.
Okay. So the excess leptons
Yes.
lead to an excess of baryons,
Which are...
the building blocks of matter.
Yeah,
Wow. It's like a chain reaction.
it is.
Starting with these sneaky neutrinos.
And it's amazing how something so tiny and elusive
Yeah.
could have such a huge impact on the universe.
It really is. And what's even crazier
Yeah.
is that the MSM doesn't just explain baryon asymmetry.
Right.
It also offers a candidate for dark matter.
Yeah.
Wait, so these sterile neutrinos could solve two mysteries at once?
They could, the lightest sterile neutrino in this model,
Yeah.
could have the right properties to be dark matter.
Okay.
It wouldn't interact much with ordinary matter.
Which is why we haven't seen it.
Exactly.
But it would have enough mass
yes,
to explain the gravitational effects we see,
that's the idea.
so we could be surrounded by these sterile neutrinos,
We could.
these tiny particles that shape the universe
Yeah.
and continue to hold it together.
It's a pretty remarkable possibility.
It really is.
But like any scientific theory,
Right.
we need evidence.
Yeah, we need to test this stuff.
Exactly.
So how do we find these elusive particles?
That's the challenge. And that's what makes this research so exciting.
Yeah.
Experiments at the Large Hadron Collider
Ah.
are looking for signs of sterile neutrinos.
Oh, wow.
The idea is if we smash protons together
Okay.
with enough energy,
Right.
we might create these particles in the debris.
So it's like smashing atoms to see what pops out.
Yeah, kind of.
And then you got to sift through all the data,
Exactly.
looking for clues.
Yeah, it's a tough job.
But people are working on it.
They are.
That's so cool. What happens if we actually find evidence for sterile neutrinos?
It would be huge.
Okay.
It would change how we think about antimatter
Yeah.
and the universe itself.
How so?
It would mean the story of antimatter is way more complex.
All right.
It wouldn't just be about opposite particles. It would be about these hidden connections
Right.
and subtle processes
Okay.
that shape the entire cosmos.
It's like we've been looking at a puzzle with only half the pieces.
I like that.
And sterile neutrinos could be the missing pieces
They could be.
that brought the whole picture into focus.
Exactly. And who knows what other mysteries they could help us solve.
Yeah, this has been an amazing journey.
It has.
We've gone from simple antiparticles
Right?
to these mind-bending ideas
Yeah.
like superselection sectors and gauge groups.
Mm-hmm.
And now we're on the hunt for these mysterious sterile neutrinos.
That could explain it all.
I feel like I've learned so much.
That's what it's all about. The pursuit of knowledge, asking questions,
Right.
exploring.
Yeah.
That's the heart of science.
Well, thank you so much for being such an amazing guide on this deep dive.
My pleasure.
I have a feeling I'll be thinking about antimatter
Yeah.
and those sterile neutrinos
For sure.
for a long time.
Yeah. And to everyone listening,
Yeah.
stay curious
Yeah.
and keep exploring the wonders of the universe.